So now we're going to take a look at the hypergeometric probability distribution. And that's a mouthful. And we're going to learn about this here in just a second. But I just want to point out that it's 9 p.m. It's 9 p.m. And I got to spend some time with my family. And I did some stuff with my kids. Now it's back to work because it's that kind of semester. And I'm recording these lectures. So here we go. Hypergeometric. So to understand this, I'm going to Control-C this URL right here, Control-C, and then Control-T to start a new tab, and then Control-V to paste that URL again. And then that brings us here to the slide. I'm going to pull that one away. I'm going to hold down my Windows key, which is where? It's right there. And then I'm going to press my right arrow, and then I'm going to select this one. And now I have two slides, right? The same slide, but two locations. Because when we get to one point, I'm going to want to look at stuff on the left and see stuff on the right. See one slide here and one right there. And then to do hypergeometric probability distribution, we'll start out just by reading this definition, which we're seeing on both slides. And this definition is this is going to make sense in a minute, by the way, why I have two copies of the presentation up. The hypergeometric distribution is closely related to the binomial distribution. So binomial, we're thinking nomial name by 2, success, failure. However, the hypergeometric distribution, the trials are not independent. So what happens in one trial will influence another trial. And the probability of success changes from trial to trial. So the probability of success changes. So let's take this here, and we'll copy just this part, and Control-C. And then go over here. If you're on Mac, it's Command. And we're going to say, please explain to me in very simple terms the hypergeometric probability distribution, and we'll just leave it at that, and we could ask more questions. Let's see what it says. Come on, ChatGPT. Come on. Hypergeometric probability distribution is used when you're working with objects selected from a finite population. So a limited population, right? Like an example that we're going to see coming up here. Let's just scroll down to that example. Here it is. Electric fuses produced by Ontario Electric are packaged in boxes of 12 each. So we'll put down, here's a note, 12 in a box. Okay, we'll just make that little note, and we'll make this bullets over here. If I could find my mouse. Come here, mouse. There we go. And we want bullets. Okay, 12 in a box. Suppose an inspector randomly selects 3. So 3 selected from box. If the box contains 5 defective in box. So we'll change the order of this because it makes more sense. So 12 in a box, 5 defective in a box, 3 are selected from the box, okay? So that's the situation. What is the probability that the inspector will find exactly 1 of the 3 fuses defective? So we'll highlight that just because that's kind of what we're going to go for. But, ooh, that's way too much highlighting. We'll go with this highlighting right here. That's funny. This is the one we want right there. Boom. 1 of the 3 fuses is defective. So we're dealing with a finite population, right? We're dealing with a population of 12, and 5 are defective in that 12. And then if we choose 3, what's the probability that we chose? Probability that 1 of the 3 is defective? Question mark, right? And we'll just color coordinate that because, believe it or not, that just helps me kind of make sense of it all. So we're dealing with finite population. So hypergeometric distribution is used when you're working with objects selected from a finite population. So 3 selected from a finite population. And the selection is done without replacement. So we pull them out, and we're not like pulling one out, putting them back, pulling it out, putting it back. We're pulling 3 out. This means that each object you select affects the probability of selecting the next one, right? So as we pull them out, this goes down to 11, right? And if this is defective or not defective, it affects the probability that the next one out of 11 will be defective or not defective. So that's a really kind of illustrative example of hypergeometric probability distribution, ladies and gentlemen. And here you see the benefits of having 2 slides. And we have this over here, but we also have this, where hypergeometric is closely related binomial. However, the hypergeometric distribution, and binomial, I guess, defective, not defective, it's one of 2 names, right? The trials are not independent, so we learned about not independent, because as we pull one out, this goes to 11, and depending upon whether it's defective or not defective, we have different probability for the next one we pull out, whether or not it's going to be defective or not defective. And the probability of success changes from trial to trial, right? So that's kind of what we're seeing there. Key features of hypergeometric distribution: 2 types of objects. There are 2 types of objects in the population, and 2 types, right? Makes me think binomial, you know, and that's where it's like saying, hey, it's kind of like the binomial, but we have 2 types. I'm going to bring this over here. And for example, you might have defective or not defective products, or red and blue marbles. No replacement. When you select an object from the population, you do not put it back. This changes the probabilities as you go. So this is the population. As we select 1, 2, 3, we don't put those back in. Fixed population size. The total number of objects in the population remains constant, right? So, you know, these are like just different scenarios you'll encounter. And if you're a statistician, you'll be like, this is a place where we'll use the binomial probability distribution. Or you'll say, this is a place where we'll use the bivariate probability distribution and those formulas. Or you'll say, this is a situation where we'll use the Poisson probability distribution and those formulas and functions, because we're dealing with an event over a period of time or over a period of distance, a length of distance. Or, oh, this is a situation where we'll use hypergeometric probability distribution. And so if you're a statistician, you just have these different kind of mathematical formulas to deal with different situations. A simple example: imagine you have a bag with 10 marbles, 4 are red, 6 are blue. You draw 3 marbles without replacing them. If you want to know the probability of drawing exactly 2 red marbles, the hypergeometric distribution helps you calculate that. Here is the formula. And if we scroll down here, right, there's that formula in action, but we could also see that formula here. So there's that. Here's that same formula. Look, oh, I just flew by it. Fx, here we use Px equal k, and then we have k over k, or r over x, and n minus r, or n minus k and n minus k. So here we have little k represents x, and so little k here would be little k, there's x, and then we have n minus big K. I'm not sure what big K is. Total number of, so they just have different notations, but it's the same one. So you can pause the video and you can just try to reconcile with the different notations there. But they're using little k instead of x. We've got x's here, and they're using big K instead of r. And so n is the total population size. So that capital N, normal notation for the population. Capital K is the total number of successes in the population, e.g. 4 red marbles. So we have 4 red marbles. Those are the successes. That's capital K. Right here, over here, they call it lower r. Number of elements in the population labeled for success is how they describe it. I like this one better. That makes more sense to me, right? K is the number of successes. That's 4. So in our example over here, and here again, right? So we could, which is the number of successes? 12 in a box, 5 are defective. And we're going to call this is going to be, we'll call this one number of successes, right? Because we're looking for defective. And that will be K in, you know, the notation over here on the left, capital K. Or it will be R in our notation right here, which is the number of elements in the population. Label for success is R. Let's just figure that out 1 second here. Capital K. Total number of successes in the population, 4 red successes. And then here we have number of successes is X. That's how many we want to go for. Number of elements in the population labeled for success is R, right? And so that would be here R. So that's the same thing. So it just took me a second to read the different language. That happens. Lowercase n is the number of draws, e.g. 3 marbles drawn. And so that's n there. And we're going to choose here number drawn, and that's going to be our n. Number drawn will be our n. And we'll do our notation here. This is the notation we're using. And n is number of draws, 3 marbles drawn. K is the number of successes you're looking for. And so the number of successes we are looking for here, this is number of successes we're looking for. In this case, it's 1, and that's going to be here. This is lowercase k, and in ours, it's x, right? So that's going to be our x. And what's the next one? And is the binomial coefficient, which counts the number of ways to choose objects. So that's just like, you know, how many different ways can you choose objects? And that brings us to permutations or combinations. And so here you can see the notation. And here you have n factorial in that notation. So really we're looking for combinations here. The order doesn't matter. And so this translates to that. And so that's the same thing here. These will translate to this type of a situation. So what are we leaving out? We've got our r, we've got our n, we've got our x, and we have x is the number of successes. We're looking for 1 success. We have n, lowercase n is the number of trials. Here we have 3 are selected from the box. And then we have capital N is the number of elements in the population. So we'll put that here, elements in population, and that's capital N. And then we have R is the number of elements in the population labeled for success. And here we have 5 defective in the box, so we have 5 labeled for success. So you kind of gotta like take a second and try to translate stuff and figure it out. So I guess maybe we could look at this formula now. That'd be a good time to do it. So here that's showing you combinations, like the different, what do they call these? They're different coefficients. And so there's notation for that right here in ChatGPT. That's what I was looking for. So this is the binomial coefficient, which counts the number of ways to choose objects. And so here's the n for combinations. Number of ways x successes can be selected from a total of r successes in the population. Number of ways n elements can be selected from a population of size n. And number of ways n minus x failures can be selected from a total of n minus r failures in the population. And you multiply those all together. So it's, you know, kind of a bit of a hairball of a mathematical formula. In hypergeometric probability distribution, the probability function on the previous slide is usually applicable for values 0 through n, discrete. However, only following values of x are valid. X has to be less than r. So the probability, the ones you draw, right? We need at least 1 success. That has to be less than the number of total successes in the population. That makes sense. And n minus x, so n, 3 are selected from the box, minus x, the number that we want successful. So 2 has to be less than n minus r, the total ones in the box and the total defective. So that also makes sense, right? So 3, the number selected from the box, and we want one of them to be successful. So 2 has to be less than 12 in the box, capital N, minus r, 5 of them are defective, 7. So 2 has to be less than 7. So that makes sense. But if you just see it written out there, you're kind of like, what? Now we have both slides on the same presentation. We have the same slide on both presentations. And so here is how you do these. And we have those factorials for combinations. So on the bottom there, we have 1 factorial times 4 factorial, which would be like here we have this thing, right? So that's for combinations. So you plug in all those numbers. And if we look at how these got plugged in, we've got 5 for our r, and we said 5 would be our r. And here's our x, and we said x would be r1, and x is r1. And then we have n minus r, which is going to be capital N minus r. 12 minus 5 is going to be 7. And we have n minus x, so we have 3 minus 1 is going to be 2. And then we have capital N and lowercase n. We have 12 for our capital N, and we have 3 for our lowercase n. And so when we do these factorials here, because this is the, what did they call it? The binomial coefficient is the name of that. Counts the number of ways objects to choose objects. That's our rule, counting rule for combinations from chapter 4. And when we do that, we get this. When we do all this calculation, so there's like a 47.73% probability that one of the three that we pull is defective. That's interesting. So that's where you'd use the hypergeometric probability distribution. And my intuition says we should now go back to ChatGPT and read this. Simple terms of explanation. Total population, there's a fixed number of objects in your group. 2 categories. The objects can be divided into 2 categories like red or blue marbles or defective or non-defective items. No replacement. You're picking a few items without replacing them. Once you pick something, the total number of items left is reduced. And your goals, you're interested in how many successes, like red marbles, you get after drawing a certain number of objects. Real world example. Let's say you're picking a team of 3 people from a group of 10. We have a finite population. And you want to know that, and you know that 6 of the 10 people are experienced workers, while the other 4 are new. What's the probability that you pick exactly 2 experienced workers in your group of 3? Right? This is a hypergeometric distribution because you are selecting without replacement from a finite group, and you're looking at how likely it is to get a certain number of successes, experienced workers, in your selection. So that's kind of like a cool thing if you're ever in that situation. You know, to be able to calculate the probability distribution for a hypergeometric probability distribution situation. So I'm just looking for my mouse again because I don't know. I need to put mouse trails on this thing because there it goes. Where did it go? Here it is. All right, here we go. So let's see the last couple of slides here. And we have hypergeometric probability distribution. The mean is going to be R over N times N. And so we know our R and we know our big N, and then this is division. It is not, that is not our, where's the math? That is not this symbol right here, R over X without a line. This has a line, so that's division and multiply. So we could calculate that, and if we calculate that, we get R over N times N. We get 3 times 5 over 12, or that number there. And then here for the variance, it's all of this, and we could do all those calculations like this, and we get that, and then take the square root of the variance, and we get the standard deviation. So this isn't something you have to memorize, or just like the main takeaways I want you to get from this is just like, hey, there's different formulas we could use in different situations: binomial, bivariate, Poisson, hypergeometric, and that will allow us to calculate the distribution of the probability when, you know, of a certain random variable, some variable randomly being chosen. We could say, hey, the probability of that is going to be this, that we get 3 of our workers are experienced, or that we get 1 that is defective out of a box of 12, or that there's this many defects over a mile of road, or that there's this many people that come into the restaurant at 10 a.m., you know, from 10 to 11 a.m. My mouse just keeps disappearing. Come here, mouse. Where are you? There it is. I got to change that. I'm going to go into here, and I'm going to go to mouse. Pointer. Let's try pointer. Pointer, mouse pointer size. And I'm going to go with a green mouse, I think. Can I change the color? Boom. That's kind of good. Ooh, I'll go with a different color. So purple, that's a little bit better. And I'll make it just a little touch bigger. That'll be easier to see. We'll go with size 2. And that's good. Now I can see it. All right. So that's, you know, you figure out which probability distribution, which type you're going to use: hypergeometric, Poisson, bivariate, binomial, or something else. And then you go look up those formulas, or you ask ChatGPT, this is my situation, which one should I use? What are those formulas? How do I calculate it? And you have the familiarity that this stuff exists. Like, that's the main takeaway I want you to get. And then being able to look it up and use it, that's the other thing. So consider hypergeometric distribution with n trials, and let P equals R of n denote the probability of success of the first trial. The population size is large. So this is just another little interesting thing that the book goes into. We're not going to go into it. All right, that's the hypergeometric probability distribution, and that, ladies and gentlemen, is chapter 5. That was a big chapter. I'm proud of you for getting through it. If you watched all these videos, I'm doubly proud of you. Yeah, so good job. Keep it up. You just keep doing the work, keep showing up, and move forward. And after a while, practice leads to progress, and repetition is the mother of mastery. You progress, and you become more of a master with this stuff. See you in the next videos, chapter and module 6. See you in the next videos.